Okay, more notes from 7.3, and this is the third thing we're going to do. Now we did the washer method, the disk method, and the washer method, and now this is finding the volumes of a solid with known cross sections. And we have a given base, we have that information. And we have almost our same formula, well, basically our same formula, volume equals area as a function of x times dx. We can also go with respect to y. We'll take a look at some of those. So let me just give you some examples here. This is basically what you're doing. So here's an example, example 6. The solid lies between the planes perpendicular to the x-axis at x equals -2 and 2. So this would be the x-axis, this is the y-axis, and I just kind of showed it in 3 dimensions so you'd see. And actually, when we're doing 3 dimensions, actually we have a third axis called the z-axis, which goes up like this. But we're looking at this, so this is going to be coming out at you if you want to think of it like that. So again, we draw three-dimensionally, and this is the 2 and this is the -2, so we'd have these planes here and here. And the cross sections perpendicular to x-axis between these planes are squares. Okay, that's squares. Whose sides are chords of the circle. X squared plus y squared equals 4. Find its volume. Now there's other ways to write this. We could say it's going from the top of this, bottom of this. And we'll talk about that in a moment. Okay, so we want to find its volume. So we have these little squares that are going from here all the way up to there. Now, I should say, if you want to see some nice illustrations of what these look like, go over to the Houston Area Calculus Teachers website and look over volumes. And I think 2 of the sections, they've got some really nice illustrations of these, okay? Because I don't have my WinPlot program working up so I could demonstrate these. I could get that going, and maybe that'd be my next project. But once I have that going, you can actually see how these work. But if you go to the Houston Area Calculus Teacher website, that would probably give you a good idea of what's happening, because they've got several of these nice illustrations in 3D or 3-dimensional. So hope that helps. So go there and look. All right. Okay, so we have this square. Now, I drew kind of an overview from the top. We're going to basically use this base for a lot of problems, a lot of examples, because there's several different renditions of example 6 that we're going to use, or variations on example 6. So we'll take a look at this. So if we look at this, x squared plus y squared equals 4, that is a circle, and the radius is 2. And if we solve for y, x squared plus y squared equals 4, so y squared equals 4 minus x squared, y equals plus or minus the square root of 4 minus x squared. As we've seen before, this positive square root of 4 minus x squared, that's the top part of the circle in terms of y. And a negative, the square root of 4 minus x squared, that's the bottom part of the circle. In other words, if we wanted to graph a circle on our calculator, we'd have to graph two functions, this function and that function. This is a function, that's a function. Together they're not, because they're not single valued, but we could graph them as 2 functions and get a circle. So if we want to find the length of this chord, or from this curve to that curve, sometimes it's notated like that, or this chord. And we did state that the cross sections are perpendicular to the x-axis, so the sides are chords. Okay, so you see that. Then if we want to find the length of this chord, we could take the top curve minus the bottom curve again. Now remember, from here to here would be positive, and from here to here would be negative. But if I take minus a negative, I get a positive, so that's going to add this segment to that segment. So that's basically what we do. So if we want the side of the square, remember the side of the square is running from the top of the circle to the bottom of the circle. If we want the side of the square, that's going to be basically top curve minus bottom curve, or the top curve minus the bottom curve, and that double negative gives me a positive. So this is basically going to be the length of this chord for any given x, and that's going to be the side of my square. And that's going to be my area. So again, we can take a look at this over here, and the volume is going to be the integral from -2 to 2 of the side squared. That's going to be the area as a function of x. The area of a square is just the side squared. And the side in this case is just this, which is this or that. Okay? So side squared. And what we can do is we can change this, because this is symmetrical. Again, this circle is definitely symmetrical, so my squares are going to be symmetrical. So I can change this from -2 to 2 to 0 to 2 and just double it. At the same time, I could square this out. So I'll get 4, and if I square the square root, I just get what's underneath the radical, which is 4 minus x squared. And I can bring this 4 out. So I just have 8 in front of my integral. Then I take the antiderivative, so it's going to be 4x, and that's going to be x cubed over 3. I'm just going to have to evaluate that from 0 to 2, and look what happens. Again, with our 0, I've got factors of 0 in each term, so the 0 goes away. So I just have to do at 2. So 4 times 2 is 8, minus, and then 2 cubed is 8 thirds. So this is 8, and then 8 is the same thing as 24 thirds, minus 8 thirds is 16 thirds. 8 times 16 is 128 thirds, so that's your area. Okay. Now we have several different kinds of known cross-sections that we use, so I tried to kind of give examples for almost everything here, so we got a lot of examples. But I'm going to refer to example 6, the same setup as example 6, but now instead of it being squares, it's going to be equilateral triangles. Okay, equilateral triangles, so one side is going to be on the circle like this, and all this other information would be given to you accordingly. So again, our volume equals the integral from a to b of the area dx. But in this case, remember the side of an equilateral triangle. We derived this in class using 30, 60, 90 triangles in our geometry. That the area in terms of the side of an equilateral triangle is the square root of 3 over 4 times s squared. Okay, I'm sorry, that's the area. The area of an equilateral triangle is the square root of 3 over 4 side squared. Well, what's the side? Well, the side was, as we showed in example 6, top curve minus bottom curve, which was this. So we just put that in the formula for the area, the square root of 3 over 4 times the side squared. And the rest is mechanics. You can follow that, I hope. And then, again, we change this to 2 times the integral from 0 to 2. And then when I square this, I got 4, and I got 4 minus x squared, and these 4's become 1. And I can take out the square root of 3 out, so I have this. 2 times the square root of 3 times the integral from 0 to 2 of 4 minus x squared. And that's going to be just over here. Take a look at this. So it's going to be 4x minus x cubed over 3, evaluated from 0 to 2. Again, my zeros disappear because I've got factors of 0 in all the terms. So I got 2 times the square root of 3, and then 4 times 2 is 8. Minus 8 thirds, and we did 8 thirds. 8 minus 8 thirds again was 16 thirds. Very similar to the last problem, or example 6. And then 2 times 16 is 32, so I've got 32 thirds over the square root. 32 thirds times the square root of 3. Okay, so that was 6b. So I hope that helps.